Today, we are diving into a really fascinating idea. What if we could take carbon dioxide, our planet's biggest waste product, and actually turn it into something valuable, something like fuel? I know, it sounds a little bit like science fiction, but some incredible new research is making it a very, very real possibility.
So this is really the big question we're tackling today. What if we could do more than just capture carbon emissions? What if we could actually recycle them? Turn all that waste into a resource and finally close the carbon loop for good. Let's really dig into what that would take.
Okay, so to get our heads around the solution, we first have to really appreciate the problem. And when it comes to CO2, the problem, in a word, is its stubbornness.
Right, here's the heart of it. Carbon dioxide is a really, really stable molecule. Chemically speaking, it's just happy where it is. It doesn't want to change. So trying to break it apart and rearrange it into something new takes a massive amount of energy, which makes the whole process super difficult and expensive.
So you might be asking, why can't we just use the chemical tools we already have? Our catalysts? Well, it turns out our old tools just aren't sharp enough for this incredibly precise job. They're kind of clumsy, actually.
Yeah, this slide just lays it out perfectly. On one side, you've got your traditional catalysts. Think of them like a gumball machine. You put in your energy and CO2, you turn the crank, and you get this random messy mix of products. Not very helpful. But the goal, what we're aiming for, is total precision. We want a machine that lets us pick exactly what we make, say ethylene or ethanol, and we want to power the whole shebang with clean electricity.
And this is where our hero enters the story. A brand new type of catalyst that promises to solve these exact problems. Everybody, meet the copper nanocluster.
So what in the world is it? Well, a copper nanocluster is a tiny, and I mean tiny, perfectly structured group of copper atoms. They're usually held together by these organic molecules called ligands. The key words here are precisely structured. We're talking about building things one atom at a time.
And that precision, well, it basically gives them superpowers. It means we get atomic-level control over chemical reactions. Because they're so small, they have this massive surface area for their size, and they start to play by the weird rules of quantum mechanics, which gives them unique chemical abilities. Plus, and this is huge, we can actually tune their outer shells to do custom chemistry.
But why copper? I mean, of all the elements on the periodic table, what makes copper so special for this job? Well, it all comes down to a unique chemical trick that only copper can pull off.
And this is it. This is copper's superpower. Unlike other metals like silver or gold, copper has this amazing ability to form bonds between two carbon atoms. Think about it. If you want to turn a single carbon CO2 molecule into valuable multi-carbon stuff like ethanol or ethylene, you have to be able to link those carbons together, and copper is the one that can do it.
So let's break down exactly how it pulls this off. First, its electronic structure is just perfect for making those carbon-carbon bonds. Second, during the reaction, it's great at holding on to these really reactive intermediate molecules, sort of guiding them towards the final product we want. And third, and this is a big one, it doesn't get distracted. It avoids making hydrogen gas, which is a really common side reaction, meaning more of our energy goes into making the good stuff.
Okay, now this is where it gets really, really exciting. Because these nanoclusters are so precisely built, we can control them with incredible finesse. It's almost like having a chemical dial where you can select the exact product you want to create.
Just look at this table. It's incredible. By making these tiny, intentional little changes to the nanocluster, we can completely shift the final product. You change the shape of the copper core, boom, you get ethylene. You swap out the organic ligand on the shell, now you're making ethanol. You sprinkle in a few different atoms, suddenly you're getting methane. This is literally chemistry by design.
And hey, don't just take my word for it. Listen to how Dr. Ahsan ul Haq Karashi from Khalifa University puts it. He says this tech gives us atomic-level control to target specific products with way higher precision and efficiency. That right there, that's the real game changer.
So, let's zoom back out for a second. What does all of this mean for the big picture? Well, it means we might finally have a real pathway to closing the carbon loop.
Now, we have to be realistic here. This is all cutting-edge research. Right now, these systems are pretty much working on a small scale in labs around the world. We're not at an industrial scale, yet.
But the vision is so powerful. The ultimate goal is to take captured CO2 and transform it into valuable fuels and chemicals, to power the entire process with clean, renewable electricity,
to create a truly sustainable, closed-loop carbon cycle. If we can get there, this becomes a practical and powerful tool in our fight against climate change.
Which really leaves us with one final, kind of mind-blowing thought. We started by looking at this huge, global-scale problem, carbon emissions, and it turns out the most promising solution might just come from these incredibly tiny, atom-perfect little structures. So, could this nanoscale engineering really be the key to reshaping our planet's entire carbon future? It's an amazing question to think about.